Hello, and welcome to the video accompaniment to Chapter 1, Section 2 of our text. In this section, negation, conjunction, and disjunction are introduced, and these are logical connectives, so we finally have a way to put together statements and open sentences. As well, the notion of logical equivalence is introduced, and a nice tool for that, which is truth tables. So if you haven't already, definitely take a few minutes and read through this section of the text, familiarize yourself with the definitions and look through some examples. And then in this video, we will express complex statements and open sentences using component statements and logical connectives. We'll determine values that make a compound open sentence true. So really this will be about making sure we understand the definitions of negation, conjunction, and disjunction. And then we'll determine when two compound statements are equivalent using a truth table. And finally, we'll apply some laws of logic to rewrite compound statements. All right, let's get started. All right, let's just take a look at an example of a couple open sentences and how to combine them using negation, conjunction, and disjunction. So we'll start with these two open sentences. P of n cubed plus 2n is even, and Q of n squared minus 4 is strictly less than 0. And here n is an integer, so it could be positive, it could be negative, it could be 0, but we know it's a whole number. So first off, not P of n. So this is using the negation, so this is the negation of P of n. This simply means just whenever P of n is true, not P of n should be false. And so how can we come up with a statement in words, or an open sentence in words with this negation? Well, the original sentence is n cubed plus 2n is even, so the opposite of that would just be n cubed plus 2n is odd. So we'll write that here. N cubed plus 2n is odd. So this is really an idea of opposite. Just like with integers, we can have the negative value of them. We get the opposite. So when they add together, they get 0. Here we have negation, which really just takes the opposite statement. This is our notion of opposite when it comes to statements. All right, similarly, not Q of n. So if the opposite of even was odd, that's how we rewrote not P of n, the opposite of strictly less than should be greater than or equal to, right? What's on the other side of less than? What would be true if that's false? If something's not less than something else, well, then it's greater than or equal to it. So not Q of n would be n squared minus 4 is greater than or equal to 0. And then notice how if I negated this again, it would come back to strictly less than 0. So negating inequalities means you take the other side of the inequality and either include the border or don't, depending on the original statement. So here is strict, so the negation was greater than or equal to. If I had a statement that was strictly greater than, the opposite would be less than or equal to. So that's the idea. P of n or Q of n. So this one we'll just write down as n cubed plus 2n is even. So in order for P of n or Q of n to be true, either one of these has to be true. Or we have n squared minus 4 strictly less than 0. So that would be that statement. Remember, this is true exactly when one of these is true. P of n and Q of n is the other side of that. This is true when both are true. Both have to be true in order for a conjunction to be true. N cubed plus 2n is even. And n cubed, nope, not n cubed, n squared minus 4 is less than 0. Right, so we're taking statements or open sentences and combining them with these logical connectives. And lastly, we have this third one, right? This isn't negation, conjunction, or disjunction. This is the exclusive or statement. So this one we'd write as n cubed plus 2n is even. And we'll just say XOR here, XOR n squared minus 4 is less than 0. So let's actually take a quick second and look at what makes these things true so that we're understanding how these component sentences combine to make these compound sentences. So we'll take a look at just P of n right now. When is P of n true? Well, let's just try a value. Let's just look and see what happens here. So how about, notice that P of 1 is the statement 1 cubed plus 2 is even. So 1 cubed plus 2, that's 3. That is not even, so this would be false. So P of 1 is false. Let's find a true value for P. What if we plug 2 in? 2 should work. P of 2. So this would be 2 cubed, or 8. Oops, 2 cubed plus 4 is even, and that one's true. And then over here with Q of n, let's find something that makes this true and something that makes it false. So let's try, how about Q of 3 would be the statement 9 minus 4, that's 3 squared is 9, less than 0. And 9 minus 4 is 5, so this is a false statement. So Q of 3 is false. And then let's try and find one that's true, maybe Q of 1. Q of 1 would be 1 squared minus 4. This would be the same thing as negative 3 is less than 0, and that's true. And I'm actually, since we're consistent, I want to be consistent here, I'm going to take, let's look at Q of 2 as well. Q of 2 would be when, so that would be 2 squared, that's 4 minus 4, so this would be 0 less than 0. And here that strictness of the inequality is coming into play. 0 is not strictly less than 0. This one is false as well. All right, so we have a couple values that make each one true and a couple values that make it false. Let's move on to the compound ones, P of n or Q of n. So what if we did P of 1 or Q of 1? So this is the statement, P of 1 was 1 cubed plus 2. So this would be the statement 1 cubed plus 2 is even, or n squared minus 4 is less than 0. So for this, we'll look at P of 1, that's a false statement, and Q of 1, that's a true statement. So the disjunction, the or statement, is true only when one of those is true, and in this case it is. Q of 1 is true, doesn't matter that P of 1 is false, Q of 1 is true, so this statement would be true. On the other hand, if we did say, yeah, we'll just leave it at that. And then P of n and Q of n, well, let's do the same thing with P of 1 and Q of 1. In this case, we know P of 1 is false, while Q of 1 is true. In order for a conjunction, the and statement, to be true, both have to be true. And so in this case, that's not happening, and so this is false. Right? This is false because P of 1 was false. All right, let's take a look at P of n XOR Q of n. Again, we'll just try it with 1, P of 1 XOR. That's a bit rough, oh well. XOR Q of 1. All right, so for this, we'll look at P of 1, which is false, Q of 1, which is true. Remember, the XOR is true only when either P or Q is true but not both of them. So in this case, it's satisfied that, right, P of 1 is false, Q of 1 is true, so one of them is true and not both of them are true. And so this would be true. All right, so this is how we can determine the truth values of compound statements. Remember that these compound statements are defined in terms of their truth table. And so understanding truth tables will be crucial to understanding these compound statements and what makes them true. In this example, we're going to take a look at two open sentences, P of n and Q of n. So P of n cubed minus n equals 0, and Q of n, 3n minus 2 quantity squared, is greater than or equal to 20, and figure out for which values of n make these true. And here we're just considering integers n. So it could be positive or negative, or 0, but just a whole number. So first we'll just figure out when is P of n true. So here we're looking at what makes this polynomial n cubed minus n equal to 0. The idea here is to factor this left side. So let's try and factor n cubed minus n. I can factor n out. We can use these algebra skills from other classes to do this. And then here we have a difference of two squares. N squared minus 1 is n minus 1 times n plus 1. N times n minus 1 times n plus 1. And we want to know when that is equal to 0. The reason for factoring this is now we can use this property of real numbers, so it extends to a property of integers, which tells us that when a product of integers is equal to 0, then one of those integers must be equal to 0. So this tells us that P of n is true when n equals 0, or n equals 1, or n equals negative 1. So one of those three has to be true in order for P of n to be true. Now let's take a look at Q of n. We could try something similar here, but first we'd want to expand the left side, the 3n minus 2. We'd actually want to expand that out and then subtract 20 and set this equal to 0, find when it crosses the x-axis, and only take things that make it less than 0. So we could do something like that, or we can just go by trial and error, or maybe you can graph it just to see. And remember, we're only taking the integers. What you'll find is that Q of n, right, sometimes it's easier to figure out when a statement is false. So Q of n is false when n equals 0, or n equals 1, or n equals 2. So if one of those three things happens, then Q of n will be false. So if we take the negation of that, Q of n is true when that doesn't happen. So the negation of this disjunction here would be n not equal to 0 and n not equal to 1 and n not equal to 2. So we're actually using De Morgan's law there to rewrite the statement for when it's false to make it into a statement for when it's true. So another way we could say this is that Q of n is true so long as n isn't 0, 1, or 2. All right, now let's take a look at some compound statements built off of these and see how to determine when those are true or false. So first we'll look at a disjunction between the two, P of n or Q of n, and we know this is true precisely when P of n is true or Q of n is true. So P of n is true only at these three values, 0, 1, and negative 1, so that's really our only chance that P of n or Q of n, that's really our only chance for making P of n true. So that'll make P of n or Q of n true at any of these three values. And then Q of n is true for all these other values. So anything that's not 0, 1, or 2. So it's looking like anything will make this true except when n is 2. So that'll be the big problem. When n is 2, So P of 2 would be false, and Q of 2 would be false. And at any other values, either P of n will be true. So for 0 or 1, that'll make P of n true. And then for any other values, Q of n will be true. So P of n or Q of n, we'll say is false when n is equal to 2. And so it's true when the negation of that happens, so it's true when n is not equal to 2. So it's true for a lot of values. The only thing that messes it up is when n is 2. How about a conjunction between the two, P of n and Q of n? Remember, P of n and Q of n is true precisely when both P of n and Q of n are true. So P of n is only true at 0, 1, and -1. So if we want P of n and Q of n to be true, we need to have P of n to be true. So we have to have, these are really our only chances, are 0, 1, or -1. And then we can go through those three options and see if that makes Q of n true as well. So Q of 0 is false. Q of 1 is false. But then Q of -1 is true. So it looks like at -1 that makes both P and Q true. So the only thing that this is going to work for is when n is -1. So P of n and Q of n true when n equals -1. That's the only way to make it true. So lastly, we'll take a look at the exclusive OR operator between these two, or the XOR. So for this one, we need P of n or Q of n to be true, but we need P of n and Q of n to be false. We don't want that to happen. So P of n or Q of n is true so long as n is not equal to 2. So that's a good position to be in. And then P of n and Q of n is true only when n equals -1. So another way to think of P of n XOR Q of n is to rewrite it as P of n or Q of n, right? We need P of n or Q of n to be true, and we need not Q of n, or not P of n and Q of n to be true. Sorry, we need that to be, we need not P of n and Q of n to be true. So since we need P of n or Q of n to be true, that's going to throw out this value n equal to 2, since we know that that'll make P of n or Q of n false. So we need n to be not equal to 2, and we need P of n and Q of n to be false. So notice that P of n and Q of n is false when n is not equal to -1. So P of n or Q of n is true so long as n is not equal to 2, and P of n and Q of n is false when n is not equal to -1. We need both of those things to happen for the XOR to work, for the XOR to be true. And so that tells us that P of n and Q of XOR Q of n is true so long as when n is not equal to 2 and n is not equal to -1. So that's the idea. That's how we can take, right? Notice how even if the instructions aren't as such to find when P of n and Q of n are first true, that would be the first good step here to figure out when, say, P of n or Q of n is true. We need to know the truth values of the component statements to be able to figure out the truth value of the compound statements those are built on. And so this is a nice method for doing that. Let's move on from this. Another key concept from this section is the idea of a truth table. So we'll need to be able to use truth tables to not only understand these definitions for our logical connectives, remember those are defined with truth tables, but also to determine when two compound statements are equivalent. And remember what it means for two statements to be equivalent is that they share the same truth value for all values of their component statements. All possible combinations give the same truth value. So let's just first take a look at the simple truth table. Here we're investigating the compound statements not P and not P. And so we'll start by just looking at our component statement P and list all of its possible truth values. So P could be either true or it could be false. And then not P column will just negate the P column. So true becomes false and false becomes true. And then not P, we will negate the not P column. So look at the not P column and just do the opposite of that. So this will be true and this will be false. So notice here that we did these two operations. We negated it twice. And the big thing to notice is that this column and this column share, right? They're the same. They're exactly the same. So it's saying that these two statements share the same truth value for all possible combinations of the component statement. And so in this case, we would say that those statements are equivalent. So we'll say here, P is equivalent to not P. Those two statements are equivalent. And this is just known as double negation. You can think of this like multiplying by a negative twice, right? Multiply by a negative twice, you get back to the original number. So it sort of undoes itself. Next, we'll take a look at this more complicated example, a bigger table here. But here we're investigating all of these compound statements here. And notice that these are based off of these two component statements. So since we have two component statements, there's going to be more possibilities than just true or false, right? We could have true and true. We could have true and false. We could have false, true. And we could have false, false. And now we'll just go through column by column and use these component statements, use those truth values to determine what the compound statement's truth value should be. So not P, I'll look at the P column and just do the opposite. So that's false, false, true, true. And then not Q, this will go false, true. Again, I'm looking at the Q column, false, true. P or Q, in order for this to be true, one of P or Q has to be true. So this will be true. So I'm looking at those two columns, P and Q. This will be true. This will be true. And lastly, in this case, they're both false. And so P or Q would be false. P and Q, they both have to be true. So P and Q, this would be true since they're both true. In this one, Q is false. So the conjunction is false. And this one, P is false. So the conjunction's false, and in this one they're both false, so the conjunction's false there. And now we're going to negate those two columns. So first we'll do not P or Q, so I'll look at the P or Q column and just do the opposite of that. False, 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 true. And then not P and Q, false, true, true, true. All right, and now we're going to look at not P or not Q. So I'll look at the not P column and the not Q column, and I'll take the disjunction of those. So in this case, they're both false, so the disjunction is false. In this case, one of them is true, so it's true. Same thing here. And in this case, they're both true, so that's true. And then we'll look at not P and not Q. So we'll take the conjunction of those two columns. They're both false here, so that's false. Here, one of them's false, so it's false. Here, one of them's false, so it's false. And then here, they're both true, so this is the only one that makes them true. So I want to turn your attention to what was the whole purpose of this is, well, see if you can see it. This column not P or Q is the same as this column, not P and not Q. And then I'll use a different color for this. I'll use green, not P and Q is the same as this column here, not P or not Q. So this is telling us two things. It's telling us that not P or Q, so if I negate a disjunction, I actually get a conjunction of the negations. And then those two columns, this is telling me that when I negate a conjunction, sort of makes sense that we should end up with a disjunction of the two negations, not P or not Q. So that's what this truth table is telling us. This is how we can pick out equivalent statements from that. And actually these two equivalences are really important. These are known as De Morgan's laws. And this tells us what happens when you negate a disjunction and what happens when you negate a conjunction. And we can use truth tables to verify those De Morgan's laws. Really, a truth table is a sort of proof. It proves that these two statements are equivalent. And that's how you do that in general, is with a truth table. We'll also see that we can use laws of logic to prove two statements are equivalent. So let's first take a look at some laws of logic, including De Morgan's laws. So we've seen a couple laws of logic already. On the last slide, here we'll just let P, Q, and R be statements, just general statements. On the last slide, we saw double negation. So this one is very handy. This tells us again that not P is the same thing as P. That if you negate twice, you just get the same thing back. De Morgan's laws we just saw on the last slide. This tells us how a negation works with conjunction and disjunction. So negating a disjunction gives us a conjunction, and negating a conjunction gives us a disjunction, or not Q. So those will be really handy, but there's a few more you should be aware of. We also have commutativity. What this tells us is that P or Q, it doesn't matter how we write this. Whenever we write something, right, we're used to, at least in English, from reading left to right. So whenever we write something, there's this inherent order in it. If an operation is commutative, it means that doesn't really matter. That inherent order is really just superficial. It doesn't matter the order in which we write them. So P or Q is the same thing as Q or P. And we could show that using a truth table, and you can get an idea of why that works, because, well, it doesn't matter whether we're looking at columns P and Q or the columns Q and P, we're looking at the same thing. And then the same thing works for conjunction. P and Q is the same thing as Q and P. So not all operations are like this, right? If you've worked with linear algebra at all, if you've worked with matrices, you know that matrix A times matrix B is not always the same as matrix B times matrix A. The matrices aren't commutative. So anytime we're dealing with new objects, in this case statements, and new operations, in this case logical connectives, we do need to verify that these laws hold. We need to explore and figure out which of these laws work. And so this slide's just all about putting out there which work and which don't. We also have associativity. So this has to deal with three statements, how we can associate. So there's associativity of disjunction, so I'll write it like P or Q. In a way, this is also about order of operations. What associativity tells us is that if we first find the disjunction of P and Q, and then find the disjunction of that with R, that's the same thing as first finding the disjunction of Q and R, and then taking the disjunction with P. That it doesn't matter the order in which we do that. It doesn't matter how we group these things. It'll come out the same. And then we also have the same thing for disjunction, P and Q. If we do that first and disjunct that with R, that's the same thing as doing P conjunction with Q and R. So that'll be nice. We can just take the disjunction of a lot of statements at once using this. It doesn't matter how we group them. And so this one is nice for actually calculating these. And then lastly, we have distributivity. So anytime we have two operations on our objects, so think like with real numbers, we have addition and multiplication, right? We know that distributive property works, right? If I want to do 3 times 1 plus 2, that this is the same thing as 3 times 1 plus 3 times 2. We can distribute that through. Notice that this is multiplication distributing over addition. That's true for real numbers, but addition doesn't distribute over multiplication. So that is like 1 plus 3 times 2 is not the same thing. It's not equal to 1 plus 3 times 1 plus 2. Right up here we'd get 7, down here I'd get 4 times 3 or 12. So those two things are not the same. So addition doesn't distribute over multiplication with real numbers, just multiplication distributes over addition. And so with statements now, with these new objects we're dealing with, we want to figure out if any distributive laws hold, and if they do, how they work. So here we want to know if disjunction distributes over conjunction, and it does. We can use a truth table to verify that. In fact, I'll have you do this in the activity. Use a truth table to figure this out. In this case, it works a lot like multiplication distributing over addition, P or Q and P or R. So in this case, disjunction distributes over conjunction. But what's true with statements, which isn't true for real numbers, is we actually get the other distributive law too. So what happens if we do P and Q or R? What happens in that case? Well, this actually distributes as well. This will be P and Q or P and R. So actually with conjunction, disjunction, both distributive laws work. So this is where we really are moving away from the algebra of real numbers into a new sort of algebra with statements, where not all the same laws apply to both cases. So on this next slide, we're gonna use these laws of logic to figure out when two compound statements are equivalent without using a truth table. So if you're really sick of truth tables, think they're really tedious, you can use laws of logic to do it. And this is going to work a lot like algebra, only we have different properties that we can use, different laws apply. So let's take a look at how we can apply laws of logic to verify the following equivalence of statements. So here we have not P or not Q, and we're claiming that that's equivalent to not P and Q. So let's, instead of using a truth table, which we could use to prove this, to verify it, let's use our laws of logic and see how those work. So we'll start here on the left-hand side. So I'll just write out the left-hand side. We have, let me actually put it over here. We have not P or not Q. And one thing we can see to do here is to distribute that negation through. That is, use De Morgan's laws to combine that negation over the disjunction. So this is not P. The disjunction switches to a conjunction, and not Q. So that's applying De Morgan's laws. And then not P and not Q. Well, I see something I can do there. Not Q, I know that we can use double negation on that. Not Q is the same as Q. So this is the same thing as not P and Q. Since we already know those laws of logic, we know that these equivalences are true, and hence we have not P or not Q is equivalent to not P and Q. So we have now verified, we have proven that this equivalence is true. And that's pretty cool. We didn't need to use a truth table to do it. And lastly, we'll look at this one. Again, we'll start with the left-hand side. So now we're doing not P, and not Q. Let's distribute that negation through using De Morgan's laws. This time it's negation of a conjunction, so it's going to switch to a disjunction. So this is going to be not P, right? Negate the first one, or not Q. Running out of room there. And then we can use double negation on both of these. So not P, that's the same as P. Still have the or. And not Q, that's the same as Q. And so now we have verified, without using a truth table, that this is true. All right, that's all I have for you in this video. I'll see you next time.